Happy Wednesday, everybody. It's Mr. Marquardt with you in a video today. Hopefully, this will help us to get through today's lesson. We are talking about the Pythagorean theorem. And after we learn the lesson today, these two jokes will make a lot more sense, dealing with hypotenuse and needing to perform a square root of a squared plus b squared section. That'll make a lot more sense at the end today for the birth of a right triangle. Other than that, let's get into it. First, couple reminders for everybody. First, we have our team problem set on Monday, so make sure we're kind of looking forward to that. Individual test is a week from Friday. I'll brush through the topics in just a quick second as well. Otherwise, we're not going to stamp homework today. Whether you have me for a teacher or Mr. Mo, we'll get you guys caught up on that on Friday, but I will put the answers up so you can check your answers to see how you did from the homework from last night. So first, here are the answers from 2.2.3. So if you want to pause the video for a minute or so, check these answers out. And here are the answers from 2.2.4, the second half of last night's homework. So again, pause the video for a quick second, check your answers out. If you can't see, part D for 98 is 0. So there's the answer for that one as well. So pause the video, take a look at those homework answers. As I mentioned before, we have our team problem set on Monday. The topics that will be on that test are angle relationships. For reference, number 40 in our white packet from last week is a good problem to take a look at for something that we might see on the test on Monday, as well as number 66 from our green homework packet. Knowing how to find area and perimeter of composite shapes would also be probably a good thing to review. And then a little transformation stuff from chapter 1, reflections, rotations, translations, and again with details like we had in our latest learning target quiz, reflecting over what line, rotating around what point, how far are we translating things, all that kind of stuff is what we can expect to see on Monday. For our individual test a week from Friday, first, the best way to study for that is to do your homework, have your toolkit filled out, check your homework answers every single day in class or on It's Learning. And then again, use those math notes that we have on It's Learning to review important vocab, important topics, all that kind of good stuff is all good. What you can expect to see is all of our angle relationship stuff we have in our toolkit. So vertical angles, what they look like, what the relationship is, supplementary angles, straight angles, what's the difference, knowing that they add up to 180 degrees, alternate interior angles, same side interior angles, corresponding angles, how those relate to transversals, and maybe in particular with parallel lines would also be important. Area and perimeter, again, rectangles, triangles, parallelograms, trapezoids, all fair game because we talked about those yesterday in class. And furthermore, a little bit more down the page here, triangle relationships, isosceles triangles and their measures. When we have two equal sides, base angles are the same, all that kind of good stuff. And then the triangle sum theorem that all three angles in any triangles will always add up to 180 degrees. And then the last couple things, graphing y equals mx plus b, so slope-intercept form of lines, solving systems of equations. We've seen that in our homework quite a bit the last couple of days, and then shapes and Venn diagrams. All that stuff is fair game for the test. So if you have any questions on that, start planning ahead, plan some time in your off mods to come to the MRC and ask for help. Ask homework questions in class of your teacher, and then start, again, working on that closure assignment too. Great ways to study for the test for next week. So today we're talking about the Pythagorean theorem. We're going to develop the Pythagorean theorem for right triangles, and we're going to prove that at the end of class. So let's open up our white packets to 2.3.2. So again, the Pythagorean theorem. We've got 299. Rory loves right triangles and has provided the one at the right to analyze. He wants your team to find the length of the hypotenuse. The hypotenuse is the longest side of any triangle, but in particular a right triangle today, which we have right here, which we could think of as a slope triangle. So AC is this one. That is the hypotenuse of this triangle, the longest side. So what I want you to do is let's pause the video here for about 5 minutes, and when we hit pause, you and your teams are going to work through 299. Make sure our facilitator is reading for our group, task manager keeping us on task, talking about math, and working through these problems as closely as possible. We'll go through them in about 5 minutes time. Read the directions carefully, and then we'll go through it in about 5 minutes. First thing we want to do is estimate the length of AC, again, which is the hypotenuse. So before we do that, I want to label the other two sides of this triangle, and we can just count the squares for those. So AB is going to be 2 units, and then BC, if we count them as 1, 2, 3, 4, 5, 6, 7 on the bottom here. So if we know the hypotenuse is the longest side, it has to be longer than 7, because it can't be the same thing. If it was the same thing, it would just be a flat line. They'd just be sitting on top of each other. So that, well, maybe not sitting on top of each other, but that is not the longest side of a triangle then if it's exactly at 7. So really anything bigger than 7 would be fine. If you put like 7.2, like 8, 9, something along those lines, that would be acceptable. We're going to find out what that is in just a second here. So Rory decided to repeatedly rotate the triangle on graph paper as shown at the right. He says the quadrilateral constructed on line AC is a square. So do we agree? So this triangle right here, that shaded one, is the one that we have on our graph paper just above here. So this short side, that change in x that is labeled as, is really 2, and this is that long side of 7. So if we rotate it around the central point somewhere in here, and we have a first rotation, second rotation, third rotation right here, the key thing is this little symbol, and again, that means a right angle. So think to yourselves, if we rotate a shape, that's a rigid transformation. Does the shape change at all? Like, does it get bigger or smaller? Does it stay the same shape? And hopefully you're thinking that it stays exactly the same. All we're doing is that we're just moving it around a point. So these rotations are the same exact shape, or we're just oriented, or it's oriented in a different respect. So all of these angles are all right angles. So we can say for sure that it's at least a rectangle because it's a quadrilateral with 4 right angles. And then if we fill in the rest of these markings, we know that all the delta x's are going to be the same length as this one down here. So this side is 2, this side is 2, and this side is 2. And then all the delta y's are the same as this one right here. Because again, it's a rotation, it doesn't change size or shape. So this is a 7, this is 7, and this is 7. So if we look at the cumulative length of all 4 of these sides and add them all up, we have a 4-sided shape with 4 right angles, and all the sides are the same measure, which is 9, because 7 plus 2 is 9. So yes, this will be a square. So now the next thing we want to do is find a strategy to determine the area of the central square. So the central square, I'm going to highlight for us in yellow. That is this one. What is the area of that? This is what we're trying to find. Area of that yellow region. All right, so let's get to it. Yesterday we talked about how to find the area of a triangle, and the formula for area of a triangle was base times height divided by 2. So if we try to find the area of the shaded region right here, area of the shaded region, that is going to be, our base is 2, our height is 7, so the area for that triangle would be 2 times 7 divided by 2. In this case, our 2's cancel, and the area for one of our triangles is just 7 units. So that's going to be important in a second. We have 4 of those triangles, so all of these areas are 7 units. I'm going to get that on there so we can keep track of that. All those triangles are worth 7. I think now, if we can find the area of the square on the outside, we can take that total area, subtract away the triangles to get the highlighted area. So if we do that, we also talked yesterday about the area of a rectangle or a square. The area for a rectangle is base times height, but in this case, the base and the height for a square are the exact same. So a different way that we can write this specifically for a square is just by saying, since these two are exactly the same, we have the same side value, but it's squared. So side squared is another way we can find the area specifically for a square, because it's the same number just multiplied by itself. So we have our sides of 9. We have our sides of 9. So if we plug that into our formula for area of a square, which again is this one, our area for the overall outside square, the one with the dotted sides on the outside, is 9 squared, which is equal to 81. So if we want to find which is what we're working towards, the highlighted square. So the area of the highlighted square is going to be the area of the outside part and then the triangle subtracted from it. So this is 81 minus 7, but we have 4 triangles, so it's really 4 times 7, so this is 28, and that is equal to, where's my notes, 53. And that is the area of the small inside part of that rectangle. Or not rectangle, but the inside part of that square, the highlighted square in the middle. That area is 53. So how can we use that area to find the side length of our hypotenuse? So again, if we look at this formula for area, we can use that to find the side length of our square. So if we plug 53 in for the area, we get area is 53 equals side squared. If we have something squared and we want to get that variable by itself, if we do the opposite, if we think like multiplying and dividing go together, adding and subtracting go together, if we have something squared, we have to take the square root of something to get that exponent to go away. So what we do to one side, we have to do to the other, and in this case, the squared and the square root offset. So we have the square root of 53 is equal to s, and that means that 7.28 is our answer for the side length of the inside part of our square. So if we slide back up to our picture, again, the hypotenuse right there of that one triangle is 7.28. So hopefully we're pretty close on that one. And if not, that is totally fine. We're going to go through that more in just a little bit. The problem that we just worked through, that method will work for any triangle or any right triangle. If we want to find the area of the inside square, we can use that to find the hypotenuse. But that can be kind of convoluted and complicated if we don't have nice whole numbers, or if the drawing is really, really big and we can't fit it onto our paper. So the overall goal today is to try to figure out a method that we can use to find the side lengths of any right triangles when given the other two sides. And again, that is what we call the Pythagorean theorem. So if we go to the top of the next page, we've got 2-109, and then if we turn the page one more time, we've got 2-111 and 2-112. So those 3 problems, we're going to spend about the next, 5 to 10 minutes. And what I want you to do is work through those 3 problems with your tables. Again, it is 109, 111, and then 112. We're going to skip 110 for today. So just do these 3 with your tables. We'll go over those in the video in just a second. So those 3 tables, you got about 10, those 3 questions, you got about 10 minutes to get those done. Then we'll go over them in the video here. Facilitators, take it away. We are working with Rory's diagram here in 299, and what we want to do is find the area of the unshaded square for this top diagram here. So again, we talked about the area for a square as being represented as the side length squared, because it's really base times height, but the base and the height are exactly the same. So how we can represent this is if we take our side length for that square, which is c in this case, if we plug that into our formula here, the area for that unshaded square would be c squared. And that is the area answer for part A here. So this part can go right in there. So Rory claims next that moving the triangles within the outer square won't change the area of the unshaded square. So what do we think? Is Rory correct or not? And I think he's going to be correct. So if we look at this diagram, we rearrange this on our page. So these 4 triangles, the shaded ones, they didn't change size, they didn't change shape whatsoever. All we did is that we took them and we moved them around, so that way they were touching in a different orientation on the triangle, or on the triangle, but that outer square, the outer square didn't change at all either. So because these 4 shaded triangles didn't change, the outside part didn't change, I think the unshaded parts have to be exactly the same as well. So what we want to do next is figure out what is the area of that unshaded part. What is the area of that unshaded part? So if we take a look at our original diagram, let's see if we can label the sides of our triangles that are next to these unshaded squares so we can try to figure out a formula that would represent the area for those. And if we look, we got the B is by the little sides. So this is B, This is B. A is by the longer of the two short sides, so this is A, and this is also A. So the area of the little squared, again, if we know our area of a square is the side length squared, then we can take the side length, which is B, and then we would say that the area for this little square is B squared, because it's B times B. If we do the same thing for this bigger of the two small squares, our side length is A, so if it's length times width or base times height, then it's A times A, which is just, again, A squared for our area. So the total unshaded area between these two unshaded parts is just going to be A squared plus B squared. And if the unshaded regions are exactly the same size, then that means they are equal to each other. So what we can say is that A squared plus B squared is equal to C squared. And that is what we call the Pythagorean theorem. And this is important, an important note here. If we take a look at any right triangle, we have to know at least two sides to use the Pythagorean theorem. But this value, C, this is always the hypotenuse. Always the hypotenuse. So these A and B values are kind of interchangeable. The two short sides of that triangle can be kind of switched around a little bit, but C always has to be the hypotenuse in the Pythagorean theorem. And that's why C squared is the largest, because it's, again, working with the hypotenuse of that right triangle. The hypotenuse is always the one that's across the triangle from that right angle, the longest side in that right triangle as well. 211 is applying the Pythagorean theorem, and same thing with 212. So again, if we have a right triangle, we can use the Pythagorean theorem to find the missing side lengths if we know two of those sides. Again, the Pythagorean theorem, A squared plus B squared equals C squared. So here we have 5, we have 4, our missing side length is X, and we want to find X. So we can use the Pythagorean theorem. Again, C squared is always the hypotenuse. So if we plug these numbers into our Pythagorean theorem, we can say this one would be A, this one would be B. So we have 4 squared plus 5 squared is equal to X squared. So evaluating this through, we have 16 plus 25 equals X squared. This is 41 equals X squared. And then to get X by itself, again, we have to take the square root of both sides. So the square root of 41 is 6.40, and that is what that hypotenuse is for this particular right triangle. So that's one application for the Pythagorean theorem. For part 2, now we got to be a little careful, because the sides that we're given, it's not A and B again, where this side length is one of the short legs, this is another one of the short legs. 11 in this case is our hypotenuse, because it's across from that right angle, it's the longest side of the triangle. So our Pythagorean theorem again is A squared plus B squared plus C squared. Let's plug in what we know. So 7 squared plus B squared is equal to 11 squared. So this, if we move it off to the side, is 49 plus B squared equals 121. And now we can solve for B. So first, we got to subtract 49 from both sides. And B squared is equal to 72. Take the square root, and we get our missing side length, which should actually be Y, is really 8.48. All right, we got 3 more to go through. Next one, 111 part B. So we got to find the perimeter of the rectangle at the right. So we're given the diagonal between 2 corners of it and 1 side length of that rectangle. So what we got to do is, again, realize that rectangles have right angles in the corners, and this makes a right triangle that we can use the Pythagorean theorem for. And we have the hypotenuse for this right triangle, which is the diagonal of the rectangle, and then we have 1 side length of 6. And we have the same exact problem as we had in part B, or not part B, but part 2 up here, where we were trying to find one of the legs of the triangle and not the hypotenuse. So what that looks like, if we set this up, I'm going to call this one, let's say X is X squared plus 6 squared is equal to 15 squared, because we don't have a lot of space and because it's the exact same process here. What we should get for x in this case is 13.75. Then as we are looking at a rectangle, hopefully remember that the opposite sides of a rectangle are exactly the same. So if we get 13.75 here, this has to be 13.75 as well. This side has to be 6. So the perimeter, adding all of those together, would be 39.5, depending on how you round that one. 111C, if you do not have graph paper, I would just draw a little cross like this. You have the y-axis, x-axis, and then we can kind of roughly plot where those points are going to be, because all we really need to know is the distance between them, both vertically and horizontally, to make our slope triangle. So if we plot point A, if this is our origin, we go over 2 spots and kind of up 6, we'd be somewhere around here. This would be A, where again that ordered pair is 2, 6. And then point C would be over 5, down 1, which would be somewhere around here. So if this is C, this is 5, that's -1. Then we can connect the dots to get the line segment between those two. And then to make our slope triangle, again, that is just telling us the rise and the run between those 2 points. So between the 2 points, our x coordinates, this is 5, this is 2, so that difference is 3. We're at 6 for our uppermost y coordinate. We're at -1 here, so this side of our slope triangle would be 7. And we are trying to find the hypotenuse in this case, which is that red side AC. So the Pythagorean theorem, setting that one up here, would be 7 squared plus 3 squared is equal to, we'll call AC, we'll just put the x there for now, is equal to x squared. So as we look, 7 squared plus 3 squared. Mr. Mo, can we do 7 squared plus 3 squared and just make it 10 squared?
Oh man, wouldn't that be nice if we could do 7 squared plus 3 squared equals 10 squared? But no, you cannot. Don't ever do that.
We cannot do that. So we have to do these first. Again, order of operations tells us we have to do our exponents first. So this is 49 plus 9, and now we can combine and try to solve for x. So do not ever combine those two and make that 10 squared. That will not work. 49 plus 9 is 58. Then we can take the square root of both sides to get x, where x, or line AC, would be equal to 7.61. And there's that one. Moving on to 112. If we drew a graph, we'd get a picture that looks something like this. We have the Garcia family taking their trip from Cowpoke Gulch. Their directions told them they had to drive 4 miles north, 6 miles east, 3 miles north again, and then 1 mile east to Big Horn Flat. So if they're starting down here, they're ending somewhere here. We want to find the straight line distance for how they traveled. So their route takes them on this red line that I have drawn here. And again, that doesn't really matter overall, because if we see that again, that this is 4 miles north, they got 6 miles east, 3 miles north again, and 1 overall. I think maybe the easier way to see this is to make one big slope triangle between those 2 points where we start and where we end. So overall, they travel 7 miles east, and they also travel 7 miles straight north. So we can do Pythagorean theorem once again, because we're trying to find the hypotenuse, which is that straight line distance right here, that highlighted line, where our Pythagorean theorem tells us we have 7 squared plus 7 squared equals, let's call it once again, x squared. And then if we do 49 plus 49 equals x squared, then we have 98 equals x squared. And if we take the square root of both sides, we end up getting that they traveled in a straight line 9.89 miles. As long as we kind of saw that overall slope picture. You could do the Pythagorean theorems 3 separate times for all those little red triangles in between, but that's probably making more work for ourselves than we need to, but you'd get the exact same thing either way. So here are the toolkit notes for today. So you want to get those green toolkits out. We got a few things we can add. I think yesterday we put the perimeter on there. We're going to add triangle inequality on Friday, so you can ignore that one at the very bottom part of the page. But we will put Pythagorean theorem and again right triangle on there for now. So I'll put my face over the definition of triangle inequality so you can't see that one. But if you want to pause the video here, get this copied down. And then last but not least, we have homework that is due on Friday, which is 2.3.1. So get that done. I know it's a little out of order, but do the 2.3.1 section first. We'll do 2.3.2 on Friday.